Yeah, g'day guys. I've decided to build a replica of a beautiful little 1920 three-cylinder radial motorbike engine. And I decided the first component I'm going to make for this Redrup Radial replica is going to be the piston. Now, just to recap, why the piston? It doesn't have a lot of interfaces to anything else. I only have to worry about its tolerance to the bore and to the gudgeon, and everything else doesn't really get affected by other design features. So that seemed like a good place to start. I've been working on this for a month. I thought it was going to be easier. Turns out I had lots of problems with shrinkage defects and had to change my gating and mold a few times, but I think I've now got it to working nicely. So let's go through and make a set of pistons for this. This project is inspired by the biography of Charles Benjamin Redrup by Bill Fernie. There's a two-view drawing of the engine in the book, so I started off by scanning that into CAD, scaling it, and then started drawing on top of it. It's a very low-powered engine, and a lot of the design features would seem pretty quaint today. The piston pin's quite tiny. There are 3 compression ring grooves, and the bottom ring seems to also retain the piston pin. Given that I want to cast these parts, having the model of the actual piston's not that helpful to me. What I need is a model of the core, which will form the cavity up under the piston. So that's what I made next. This core mold went through a large number of iterations, both to improve the geometry so that it would release the sand better, and also because I needed some slight tweaks in the final dimensions for machining. Pre-form the pin bore, I made a second sand core. This one's got a flexure sort of design so that it's quite easy to demold once the sand's been hardened. And then I needed a pattern to form the outside geometry of the piston. This also went through a number of different iterations because I was getting a lot of shrink defects between the risers and those web-shaped runners across to the actual pattern itself. In all, it's taken me 7 or 8 casting sessions to iterate away all my errors in the mold and pattern design, match plate layout, casting practice, melt temperature control, machining allowance, etc. So this video captures the lessons learnt from the last 3 casting sessions. I've got previous videos covering the earlier stuff. To make up the somewhat complicated internal features of the piston, I made up this 2-piece core mold and a pin driven through the middle. Before I fill it and ram it with sand that's mixed with a little bit of sodium silicate. The cool thing is that contact with carbon dioxide hardens sodium silicate nearly immediately. So if I just blow some soda stream carbon dioxide through my sand, I get a nice hard sandcastle. I added some extra holes around my mold to allow me to blow gas into the more difficult to reach parts. So that core forms the inside of the piston, and this pattern forms the outside. I've still got a good number of pouring basins and riser extensions, but I'm starting to get low on pin cores and piston cores, so I had to make a bunch more of those as well. Well, I've done plenty of sandcastling because each piston needs a main piston core, a pin core, a pouring basin, and 2 risers. So 5 little sandy things per piston, and I want to make 12 pistons. Since my earlier pattern designs having problems with shrink defects, figured I'd cut one open, polish it up and etch it just to get a better look at what's going on. Really, I've probably put a wee bit too much machining allowance here. This is 10 millimeters across here, and the final machined crown is only 4.5 millimeters thick. Down here as well, I've definitely got probably more metal than I need. So for my next attempt, I've reduced the diameter of the pattern and also reduced its height, which will take away that extra metal. I also dropped the height of this button, which I need for machining. That can also be smaller than it was. And I increased the thickness of the runner from 3 millimeters to 4 millimeters because it was filling extremely slowly. Because I put the gating and runners on a match plate, each time I iterated the design, I had to modify it. Okay, so reducing the machining allowance does seem to have improved the shrink defects a bit. One of them seems to be very minor. The other one also better than they were before. Looks like we might have moved the shrink defects a bit further out into the web. So generally a good thing. But we're still trying to improve that. So now we're going for really big risers here. This is up to 27 millimeters. It's about as big as I could do without changing all of the radius geometry and stuff. And this became my final design. The last bit of tooling I needed was this simple mandrel that's going to get used both on the lathe and on the mill to hold the parts for machining. Now for my piston casting, I've been using this flask, but unfortunately it's actually a couple of millimeters too narrow and therefore not getting a nice clean strike off over my patterns. I think I'll make up a replacement, or maybe even two if I've got enough wood. I've got this old IKEA shelf. It's good enough. They'll get burnt up anyway. There's some pieces of metal in the end of it, so I need to cut the ends off. Next I need to square up one long edge. Let me just double check that before I cut any more. So 7/10 over. Okay, that's about as good as I'm going to get it with wood. It's a pretty accurate saw, really. Right, the short boards need to be 220 millimeters and the long ones 320. Right, now I'm going to need a stop block. Right, so there's all the short ends. A little rebate in the corner of the short ones will make them easier to assemble. Three millimeters, that should be enough. These will probably work fine, but with just flat sides like that, you always risk the problem of having a sand drop out. You've finished your whole mold, and just when you pick it up to put it somewhere, the sand slides off the wall and falls. That's why on this, I've got these recesses milled into the sides of the flask. They don't look that great, but it just gives the sand something to tooth into on the sides so you don't get dropouts. Well, I can't remember exactly what setup I used, but I'm pretty sure I used the router. I'm going to guess I used this sort of guiding plate. It really doesn't take much. That's probably only 1 millimeter deep, but that'll be enough to hold the sand. Alright, the last thing, I need some alignment hardware. I'm too lazy to make a new set every time, so I'm just going to take it off this one, which means this one's probably never ever going to be used again and will probably sooner or later end up in the fire. I'll just knock the anchor nuts out and reuse them as well. So what should you make pistons out of? If you go on the internet, there are all sorts of suggestions of how to get aluminium for casting. Some people seem pretty keen on melting down old Coke cans, while other people think it's a good idea to remelt down the chips. But remember, aluminium is a very reactive metal. So whenever you're looking at it, you're never seeing the metal. You're only ever seeing the oxide coating. And aluminium oxide is extremely stable. Whenever you put aluminium in your furnace, the alloy you want will melt out of that oxide layer, leaving that skin behind it. It's called a bifold. The smaller the bits of aluminium you start with, the worse the ratio of good metal to bifolds, aluminium oxide skins. So don't use this. Just take it to recycling. Another source of aluminium you really want to avoid is extruded aluminium. Anything that's wrought, forget it. There are much better alloys to cast with. Now, if you're going to do a general purpose casting, start with something that's cast aluminium. Something like a cylinder head, car wheels, anything that was originally cast is probably going to be a pretty good alloy. But we're not doing a general purpose castings, we're making pistons. And pistons are made out of special alloys. They're typically high silicon alloys, up around 10 to 12% silicon. I was generously given some pistons which were a superseded part number and therefore were not going to be used, so I appreciate that. Thanks very much, guys. And this is, I think, a 10% silicon alloy. Now, while my garden shed may look like a pretty typical little gardening implement shed, that's just cover for its secret life as a fully equipped foundry. I'm able to do aluminium, bronze, and even cast iron with this furnace. Just need to mull the sand with a bit more water because it's a bit dry at the moment. I reckon even more than a good furnace, a muller is essential for enjoying home foundry work. It takes a lot of the effort out of it. After a while, you sort of get a feel for how the sand should feel if it's got the right moisture content. The match plate gets parting powder so that the sand doesn't stick to it, and I try and sift the first layer of sand because it makes a much nicer finish. The rest of the sand that goes in doesn't need sieving, just fills the mold, and then initially I use the sharp end of the rammer to try and force the sand down into the corners and into the edges, and then it's just a matter of beating it into a nice flat surface. After striking off, the drag is finished, and that's the easy side. The cope gets the pattern and also the sprues which the aluminium runs into the mold through. Ramming the cope on this pattern is much more tricky. You really have to get in there and massage all the sand down to follow the contours nicely, especially those thin webs which form the runners between the risers and the main piston pattern need to be rammed really quite hard. And to massage the sand up under the lip which the core sits on, I found it's best just to use my fingers. When I first started casting, I didn't put much effort into things like designing the sprues and cleaning out all this air and keeping sand away, but Martin, the old foundry guy, has given me a lot of good tips and has really improved the quality of my castings. Martin taught me to use a lot of parting powder after removing the patterns so that if loose sand does fall in, it shouldn't stick to the other sand. It makes it much easier to blow it away. I used to really rush this part of the process, but Martin's taught me to slow right down, take the time to try and avoid loose sand and also to blow it away, and just generally good mold hygiene. A little bit of extra effort at this point saves you a lot of scrap castings later on. I need to install the little pin cores into the main cores and then put them into the mold. And when doing this, I do sometimes knock a little bit of sand into the mold. Something I never used to do was reopen a mold and clean it out again, but that really helps as well. There's always a little bit of sand falls in that you can clean out. Over multiple iterations, it turned out these risers of about 30 millimeters were perfect to give the right head of pressure for the aluminium. It's important to weight down the molds and also these cores. Sand is less dense than aluminium, so it floats on it. It would suck to have the core float off, destroying a casting after all this work. I'm using some boron nitride spray just to prevent the melt from attacking the stainless steel of the spoon, which I use to scoop out any dross. A few years ago when I was first starting this channel, I did a video on my foundry. I designed it to take an A20 crucible at a pinch, but these are just like A8 or A10 or so. And while I do have a waste oil burner, I find that too powerful and not really controllable enough for fine aluminium castings like this. So I tend to do these with just propane. Ideally, I want to be pouring these pistons at about 570 to 590 degrees according to my thermometer. It's very easy to overheat the melt. And then you got to wait for it to cool a bit, and time at temperature increases porosity. Okay, let's go. Now, while I only need 3 good pistons, I've been through a number of iterations trying to sort out my technique, and most of those sessions involved multiple castings, so you can see I got lots of different angles. The game's not about filling the mold as fast as you can, but really you want a nice controlled flow of metal that's not too turbulent. So the pouring basins are matched to the sprues to hopefully give a nice low turbulence fill. Once the castings have solidified enough to be demolded, I try and be a little careful and keep most of the coarse sand out of my main sand pile. Demolding and then quenching while the parts are still nice and hot assists the later heat treatment process. Here you can see the result of the final casting session. I started out with 12 sets of patterns. The first two I went too low on the pouring temperature, so they didn't pour nicely. They got remelted. One of them I got a cold shut, so I'm left with 9. Well, you can really see that high silicon alloy really likes to shrink. I made the risers bigger, the runners shorter, and reduced the machining allowance over multiple iterations of this pattern to try and get the shrinkage out of the parts. Pretty happy with the general quality of the castings. Right, let's degate these and see what they look like. Well, at first look, at least it seems like intact metal all the way through now. Cool. Right, now they're degated, they need heat treating. So they'll be going in the oven at 200 Celsius for 8 hours to bring them up to the T5 heat treat. So this is the surface finish after heat treatment. And that's the same insert, same speed, but without heat treatment. As you can see, it definitely makes for a better surface finish. So what's my machining strategy to actually get this out of one of those raw castings? At first I was trying to work out how to do this in the absolute minimum of setups, but then I watched one of those excellent tutorial training videos from Pakistani manufacturing, and then I realized you can do plenty of operations, it's no problem. So we first want to fixture off that core and rough turn the outside cylindrical or parallel with it, so then if we grip it on the outside we'll still have the core running around. So my second operation is going to be cleaning up that. Once I've got that reference surface done, that's when I can locate things like my piston ring grooves. While it's in the middle doing the pin bore, I could do the skirt cutout, but because it has to go back into the lathe afterwards, I don't really want to be gripping across that cutout, so I think I'll do that after decking the crown. Now, I mentioned in a previous video that pistons are neither round nor cylindrical, and I was asked to explain that. So if we take a look, this is where all the fire is. So this part of the piston's going to end up hotter than down here. And therefore, rather than being a simple cylindrical shape, you actually want the piston to be more cone shaped, highly exaggerated here, because this is going to expand more because it's hotter than this part. So we're conical along the bore. And then the second thing is, rather than being round, we've got more mass around the piston pin locations than we do across it, and therefore you're going to get more thermal expansion this way than this way. So ideally you want your piston to be kind of egg shaped, with this dimension being smaller than this dimension. Mail time. One of my kind Patreons, Julian, sent me a couple of diamond insert cutting tools a couple of weeks ago, and unfortunately he said he sent me the wrong one, and it was one that was already worn out, and he decided to send me another one, so I think that's what I got here. Yep, a monocrystalline diamond cutting tool. Wow. Let's see what it does for a surface finish. For this I'm going to max out my spindle RPM, 3000. You want extremely high cutting speeds with these things. Wow. That monocrystalline diamond which Julian gave me leaves amazing finish, doesn't it? Thanks very much for that. Since the core carries all the most important features, I first have to face off the tip of it, and then I can center drill it so that I'll be able to support it with the tailstock. The advantage of doing it this way is once I turn down the OD, it's going to be parallel to the core, and while I'm at it I can also rough in the piston crown. Here you can see why I cast many more pistons than I knew I was going to need, because this one had a course shift and didn't clean up. All the others I turned to 52 millimeters, so there's 1.2 millimeters on diameter still to go. This one I've taken down to 51, and yeah, there's no way it's cleaning up, so that one's scrap. What I am really happy about is all of them have cleaned up with no shrink defects so far. Nice. Okay, now I can flip these around for operation number 2, and that is to turn down to this mark here, which acts as my indexing point where all the measurements will be taken from. Might have lost a second one there, because this one's got a defect in the skirt. That's probably not going to be cut away. Yes, that's probably also a reject. Now with the mandrel mounted, we've got about the most important operation, and that's turning the OD down to the correct dimension and putting in the ring grooves. Okay, well, that had been working properly, but my guess is it's now got really blunt. So I need to resharpen that tool, because that made a hell of a mess. Scrapping one of my pistons. Bugger. After this, to prevent any further damage to that high-speed steel cut-off blade, I dropped the RPM for that operation a bit, and also re-honed the cutting edge after every single piston. So aiming for 725, that's 1 micron over. The fourth operation is to drill, bore and ream the gudgeon pinholes. Earlier on I did this before turning the outer diameter and doing the piston rings. Later I decided to switch those two operations around. Well, I no longer need this centering spigot, so I can zip that off. And now I can also face them off to their final length. Looking at these three, they have quite bad porosity in their crowns. These ones look much better. There's a wee bit there and there, but nowhere near as bad as those ones. I was using one of my scrap pistons to set up the facing operation, and hands up if you're disappointed that I didn't have a camera going when I produced this little disaster. I had a wee bit of chip out on the back of the skirt, so this next operation I'm just going to clean that up, slightly shortening the skirt. The sixth operation is just to relieve the skirts under the pin bosses. I think that's done to reduce friction. Piston pivots here, so perpendicular to the pin bore you need the long skirt to guide the piston, but under here it really doesn't do anything. You can see here that I've kept a number of my defective pistons because they're excellent for doing this kind of setup work, just trying out toolpaths and stuff. Okay, so after a bit of playing around, I think I've got a toolpath that's going to work. So for this toolpath, first I do a clearing cut to get rid of most of the waste that I don't need. While it's on M1 stop, I index my rotary table around by 55 degrees, unpause it, it goes down, cuts the radius corner, goes up to the inner corner of the cutout, pauses again. I start indexing around to 55 degrees in the other direction. As I go through the center, I unpause it so that the tool can move from +5 to -5. 10mm tool. Then it continues to the far end and cuts the radiuses on the other side. And then I just drop the part out, index it round to the other side and do the same thing again. This would be a perfect job for a CNC integrated fourth axis. And I have of course considered removing the handwheel from this and mounting a motor of some description, but the feedback I've had is that a lot of these cheap rotary tables don't have very accurate gears in them, and therefore it's probably not an ideal machine to start with. I've kind of been keeping my eye out in the classifieds and that to see if I could pick up a proper Niken or something like that. You know, a CNC rotary table for a decent price. I need something pretty small, like 160mm or so. So far I haven't seen one. Well, I'm pretty happy to have that finished, but of course a job's not done until tidy up's finished, so let's just clean down the mill. After all that, I've ended up with 4 good pistons in dimension, one of which has got a very, very slight defect on it, but otherwise these ones are pretty good to go. I've got 6 seconds which have minor dimensional tolerances or other slight issues, but probably good enough for a cutaway engine. And then I've got 3 scrap ones which have got defects that didn't clean up or major inclusions and stuff in them, which will be good for fitting out and other things later in the project. Now, I didn't nail dimension on any of my pistons perfectly. I was aiming for 725 up around the crown, which is 3 thou under nominal, and I was aiming for 750 across the skirt here, 2 thou under nominal, with a thou smaller across here, 725. I've got a little bit too much ovalization, a little bit too much relief across here, which is more like 4 thou. It was supposed to be 3 thou. But all in all, I'm pretty happy with the pistons that I've manufactured. They're not perfect, but they're good enough to move on with the rest of this project. And I'm really looking forward to that. And if you're enjoying the project and would like to help support the channel, I'd really appreciate it. There are links for both Patreon or Buy Me a Coffee down below. Thanks a lot for watching, and I'll see you next time.